Welcome back, folks, to another edition of Integrated Chemistry Physics. Today, we're going to dive into our second unit already. We are going to be talking about video 2-1, which focuses primarily on motion. By the end of this video, you should be able to understand and explain motion, velocity, speed, distance, and displacement. You should also be able to calculate velocity, momentum, and distance, and differentiate between speed and velocity. So let me give you a brief introduction here. A cheetah can run at a speed of 120 kilometers per hour. That's pretty fast. That cheetah's clocking in at about 75 miles per hour, if that helps. A horse can run 64 kilometers per hour, which is about 40 miles an hour. And a tortoise walks 0.3 kilometers per hour. I wish it said tortoise runs, but, tortoises don't do that very often. The speed is determined by taking the distance and divided by the time. How does your speed compare to the speeds of these animals? So, I don't know very many people that can go 75 miles an hour unless you're in a car, nor 40 miles an hour unless you're the person riding the horse. Top speed sprinters, Usain Bolt and the like, peak out at about 24, 25, maybe even 28 miles an hour, but that's for a really short distance. So think a little bit about where you fall within this and what your velocity might be. Let's talk a little bit about motion. Motion is just a change in an object's a change in an object's position relative to a specific reference point. So in the picture on the right here, the car is what is in motion. If your reference point is the tree, the reference point stays stationary and the car moves. You could argue, though, that if the car is your reference point, that the tree moves backwards. All of it just depends on simply what you refer to as your reference point. And we can use a coordinate system like a map that allows us to find different distances and reference points, just like what you've done in your algebra classes. You're able to determine the distance of 2 points based on where they fall on the coordinate system. Now, a lot of times in physics, when we're talking about motion, we'll use a reference point and call it 0, and then based on whether it moves forward, whether it moves backward, that helps us understand more about motion, movement, and eventually speed and velocity. So let's talk about distance. Distance is just simply the length of travel, which is measured in meters or longer distance kilometers. For example, 100 centimeters is equal to 1 meter. The way I always remember that is cent. There's 100 cents in a dollar, so 100 centimeters in 1 meter. And then milli means thousand, like millennial or millennium. There's 1,000 years in a millennium, so that equals 1 meter. Just a couple of real easy conversions that you may want to always know. Now, distance is always positive because it's always how far we are away from our point of origin. We don't really have a direction per se. So whether I go north, south, east, or west, my distance is always going to be positive. My distance is just simply how much I've traveled. I could go from here to school. I live about 10 miles away from school, and then back, and I would say that my distance covered is 20 miles. Or in the example here, going from home to school and back, your distance is 10 kilometers. Now, displacement is a little bit different because this includes the change in an object's position as opposed to how much it's traveled. Let's look at the example on the right in terms of displacement. You travel 5 kilometers to school, but you also travel 5 kilometers back. You initially started at home, and your final position is at home as well. So did you ever truly change position? And the answer is no. You did not change position, so your displacement is 0 because you ended up in the exact same place where you started. Displacement can also be negative as well. Let's say I go 5 kilometers the opposite direction. Well, then my displacement would be negative 5 kilometers because I went the opposite way. But I'll say it again. Consider that you walk 5 kilometers to and from school. The distance traveled is 10, however, the displacement is 0 because your final position and starting position are the same. Speed formula is distance. An object travels over time, and that is the distance divided by time, and you get a formula unit of meters per second. A car is traveling at a constant speed of 750 meters in 25 seconds. What is the car's speed? Well, remember, the speed is distance over time. The car travels 750 meters, so that is my distance, and my time is 25 seconds. So I'm going to take 750 meters divided by 25 seconds. And what I get is 30 meters per second. A motorcycle is moving at a constant speed of 40 kilometers per hour. How long did it take the motorcycle to travel 10 kilometers? Well, in this instance, this is our speed, this is our distance, and our unknown is time. So we'll plug those in and solve. 40 equals my distance, 10 over time, x. In order to solve for x, I need to multiply x out of the denominator. So I end up with 40x equals 10. And in order to solve for x, I'm just going to divide by 40 on both sides. X is going to be 0.25 hours. All right. And if I were to ask you to convert that to minutes, you'd be able to do that as well. And we'll go ahead and call that our answer. But if, let's say I wanted minutes, we do dimensional analysis. Hour to minute, 60 minutes in an hour. You multiply, and what you get is 15 minutes. Okay. Pretty straightforward on how to do those types of problems. Just make sure you know how to plug in your numbers, identify variables, and solve. We can utilize graphs to look at constant speed versus changing speed. So as we see, we start with 0 kilometers per hour, and our speed increases, which means we are accelerating. Once we hit a peak, that is when our speed is constant. When we go back down, we are decelerating, or our velocity or speed is getting slower. So you can see at the third peak, we got up to about 11 kilometers per hour and stayed that way. We had a constant velocity at that particular time. So when you have 0 velocity, the object is at rest and no longer in motion. So you can describe this graph, right? We started at 0 kilometers per hour and we accelerated to 20, we decelerated to 10, then re-accelerated back to 30, where we decelerated back to 0 and stopped. We then accelerated back to 11 kilometers per hour and held that velocity for a certain period of time, and then we then decelerated and stopped at the very end. Distance versus time graphs also show a variety of factors and changes in motion. So let's take a look at the green line here. The green line just shows a fast and steady speed moving from 0 to 100 meters in 5 seconds. The difference between this graph and the previous graph is that on the y-axis we had speed, but in this instance we're looking at distance. Because the slope of the green line stays constant, it is at a steady speed. We are moving at a rate which is constant. The blue line, however, shows a journey with a stop and return to the starting position. So we start motion, it's constant motion, steady speed because we have a line. We then get to 40 meters after about 5 seconds, and then the slope is 0. Well, that tells us that we have stopped, that there is no motion because the distance stays the same. We then take a steady speed back to our starting position, again, because it is a straight line. The red line shows acceleration and deceleration because it is not a straight line. As you accelerate, your velocity increases. That would be indicated by a line on the graph that is linear. In this case, we don't see that. We see acceleration, where the velocity increases. You could probably see a part of the line that is linear in the middle between the words accelerate and decelerate. Notice that it starts to curve as the velocity decreases, and then eventually we have a stopping point where no more movement is taking place. Keep in mind that velocity and speed are not the same thing. Velocity includes speed and direction, so it's very similar to the argument for distance versus displacement. Distance is just how far you've moved since the starting point. Displacement is the final minus initial. Velocity includes speed and direction. So this can have a negative and positive value that is relative to your starting position. So velocity and speed, again, very similar to that of distance versus displacement. Motion is relative to velocity and the reference point. For an example, I like to look at the highway as an example, and let's say we're barreling down 74. If you're going down 74, you may have a speed of 65 miles per hour. But the car next to you may be traveling 70 miles per hour. So it's going to look like that car is traveling at 5 miles per hour because it is going 5 miles per hour faster than what you are going. It's the same thing if we look at an example where you are traveling 70 miles per hour and the car next to you is traveling at 65 miles per hour. It is going to appear to be going -5 miles per hour in the reverse direction because of your reference point. So again, motion is relative to velocity and whatever you decide is the reference point in which you're looking at it. Momentum just refers to an object's velocity and mass. When two cars collide, typically they're going to have very similar momentum because they're traveling at the same velocity and have the same mass. But as you know, if a big semi-truck runs into a car, typically the damage is more on the car than it is on the truck. The reason being is that the object has more momentum because momentum is the product of velocity and mass. The formula below, in order to be able to solve for that, it would be the same concept as before. You just need to be able to plug numbers in and solve for momentum. Hopefully you got a lot out of this video and you understand the student learning objectives. Again, please keep in mind those position graphs and understand the difference between distance, displacement, velocity, and speed, and be able to calculate anything using variables that we've looked at in this particular video. We'll see you next time. Have a great day, guys. We will talk to you later. Bye-bye.